Um, so the topic I picked today is specifically this. I've got this guy that I have interacted with on Facebook and LinkedIn and a number of other things named Jason Brownlee, who's a PhD in data science and machine learning, artificial intelligence. And he's just a really smart guy. And at some point, he just started a blog. And the guy writes about 2 or 3 blog posts a week that are really focused on application development. So they're really more for engineers and for developers, right, than they are for academics. And I find this site incredibly useful as someone who is not a math major. I'm pretty strong mathematically, but I am by no means a PhD or even a master's in mathematics. So a lot of times I just have a problem I want to solve, and I'm constantly trying to add tools to my toolbox on how to solve those problems. And usually those problems fall into a couple different categories. They're either classification problems, or they're forecasting problems, or they're you know, just how to get something from point A to point B, engineering type problems. A lot of it is like decision making type stuff, and statistics is like the key thing that's used for automating decision making, right? This guy is really focused on machine learning and artificial intelligence, techniques. So neural nets, SVM, any of the characteristics that you would use, any of the algorithms that are really used in automating statistical analysis and statistical output. So this blog itself, literally, if you just start about stuff, you can literally just start reading it or do a quick start guide, and he will get you pretty far pretty quick with this stuff. He's even got a thing on here, understanding algorithms, and he gives a pretty good overview of the different types of algorithms, the different use cases for them, linear versus nonlinear, right? So these all are used for solving different types of problems, right? And that's kind of what I wanted to cover. So most of these linear algorithms are forecasting related, right? They're designed to tell you in the future a value you predict what a value is going to be. This is like your crystal ball kind of stuff that says this is what I think it's going to be in the future. Then an immediate thing that people come to this is like, oh, I want to use it on stock prices. Well, it's more complicated than that, because it's not a guarantee, right? You might not have enough information to make a good prediction. The other thing that people are probably most familiar with when you're talking about any sort of forecasting algorithm is weather, right? So everybody's seen like the hurricane path thing, and it's got the line that goes straight into Florida, and then it's got all of this cone of uncertainty basically that shows, well, we're 90% certain it's going to land in Miami, but there's a 15% chance it lands in the Keys or whatever. And these kinds of algorithms for forecasting do that. Then the other thing, most common thing that you use with statistical algorithms is classification, which is basically labeling things or putting them into buckets for, whatever you want to use that label for. A lot of times, so when people think of like artificial intelligence, robots, a lot of that actually ends up being a combination of the two, and combining various different algorithms to accomplish some sort of goal. So like the robotic arm that catches things, that's a combination of forecasting where the ball is going to be that the robotic arm is going to catch, and then a classification of like what grip to use to catch it when it gets there, right? Because maybe it's a different type of ball, you need different kinds of, whatever. So you classify it. It also comes in really handy for cat pictures, right? You get like 500 cats pictures, and you want to classify the type of cat. Like those are classification problems. And then the other thing that's really common is clustering algorithms, where you don't know what the classifications are. You don't know what the groups are in a giant pile of data. You just know that you have 5,000 images. But what are they, right? Are they cats? Are there dogs? Are there more classifications than just cat and dog? And what you would do with that kind of data set is use a clustering algorithm to identify subcategories within that group, right? So you would come up with it. It helps you define the buckets that you would use to put those things in. So you use the clustering algorithms to identify and explore the data to define the classifications, and then you use the labeling algorithms to put a label on them after you've defined what labels to use. So those are the three biggest categories I can think of off the top of my head. But he goes into, and there's a million different ways to do all of these things, right? There's linear algorithms that are just a straight up, time series, and then there's multivariate forecasting, which uses, multiple variables in trying to predict a specific value. Linear, most people are pretty familiar with, just because there's a straight line, like you see a bunch of data on a chart, and then you take a pencil and you draw a line across it, right? That's an algorithm. It's not a very good one, but it is an algorithm. Or you might use something that's just a stepwise calculation that basically says, in January it was 5, in February it was 10, and so my forecast is that March will be 15. It's a pretty stepwise, straight line, linear, forecast. So those are regressions, right? So anybody that wants to get into this stuff, I strongly suggest you literally just go to this guy's page and start reading. Step 1, discover the mathematics statistics methods. Discover the statistical methods are important for machine learning, because anything anybody talks about when they start talking about AI or machine learning or any of these kinds of things, most people don't seem to understand that all of it is automated statistics. Most people think it's some sort of like magic or special thing, but that's really all it is automated statistics. So then, yeah, there's a lot of stuff to read there. I don't buy books personally, because I feel like everything that they have to say is already online, freely available. If you know what you're looking for, you do enough tutorials, then you get a concept, and then you can Google it and find out more about it and grow and grow and grow. But if I was going to buy a book, I'd consider buying his. So then a lot of what, the topics that end up getting involved in data science and data engineering end up being around data cleaning, monitoring, analysis of variance, like is this normal kind of checks, and data quality, how to validate the model that you've built to confirm that it is doing what you think it is doing, and how accurate is it. And there's a lot of, methodology depending on how much data you have and what type of data you have. Is it, linear, or is it discrete in that, it's like labeled cats, dogs, elephants, whatever, or is it numerical, like a temperature, like ranges from negative whatever to 300,000 million degrees, or so there's different types of data, and different types of algorithms work on different types of data. So that's my short introduction to this website. It's a great website. You can get lost on here for years. Literally, I've been reading it for years. So back to his blog, right? So he does a lot of tutorials on a weekly basis, and he'll pick a blog. He'll pick a specific algorithm and a specific methodology to try to explain how it works and why it works and when you would use it. And then he even gives you the code necessary in order to execute it. So there's lots of different types of regression, which is a specific type of forecasting, which is kind of similar to what I was talking about earlier. And there's this keep in mind, this is all in the context of machine learning, which is automated statistics, right? So what makes it automated? So in this, I'm just going to use ridge regression as an example in this to talk about the general concept here. So it's an extension of linear regression that adds a regularized penalty to the loss function for training. So there's, just in that one sentence, there's a lot of information loaded in there that probably sounds like Greek to some people. It adds a regularized penalty to the loss function during training. So first of all, you have to understand the concept of training a machine learning model, which basically consists of same thing you do in statistics. You have your data set, you create a prediction, and then you use some of your data to test whether or not you had a good prediction. It's really that simple. And when you automate it, it adds another level to that. When you say, what is my testing? I'm automating my testing for my machine learning so that I can then tweak the statistical model automatically, right? And the loss function is that test of how good is my model. That's what a loss function is, essentially. And what he's saying is that rigid regression is a very specific version of regression in machine learning where it adds a regularization penalty to the loss function. So what that means is basically it minimizes the coefficient in the equation. So he's saying the bigger the coefficient, the less quote accurate the model is considered to be. Because it, when you have big coefficients, then the statistical model has a tendency to kind of like fluctuate wildly and becomes quote, they call it unstable, in that it may look good historically, but moving forward, this model's not going to work very well, right? It's not very good, got good forecasting ability. So it'll look good on your test data, but won't look good in on your future data. So ridge regression is attempting to minimize that impact. So, and then he kind of goes into linear regression, and he talks about the loss function here. I already read this article, that's why I'm kind of summarizing it. And then, he gets into the math, which I'll skip, because I know probably a lot of you don't care. And then he gives an example. And he's got this data set here. I actually didn't open the data set. So here's your data set here, right? So the way to look at any of these kind of data sets is columns and rows, right? Your columns are your variables, and most people are familiar with Excel, so that makes sense. And then your rows are your samples, right? So this is a housing data set, so this is one house per row probably. And I imagine that a lot of these are like, I'm sure he has a data set definition on here somewhere that says what each one of these columns are, but I imagine they're, latitude and longitude, location, and then maybe pricing information on the house. And, who knows what this column is. So you would take a data set like this and you plug it into a machine learning algorithm that then basically generates a formula to create a forecast of what it thinks the future value of this thing would be a month out or whatever. All right, so I can kind of demonstrate the concept of forecasting a little bit better here. I pulled up one that we built for the clinical data coordinator role, right, to forecast how many contractors do we need, right? So you can see on the left-hand side here, we got month, and then there's a bunch of variables along the top here, right? And column M is my forecast. Question is, what am I trying to forecast? I'm trying to forecast like quality of and deliverability of the team. Like how good are they at delivering that month? And how much do we expect them to be able to deliver?
Are you sharing the Excel?
Oh, I am. I'm trying to. Let me share here. All right. All right. So there you go. Can you see it now?
Yep.
All right. So over on the left side here, start over here. On the left side here, you got the month, right? And then along the top, you can see the names of all the variables that go into this formula that we've developed. And this is our model, right? So this formula up here is our model of how to calculate our forecast. And it's a multivariate formula that basically has a weighted function on how much does each one of these columns feed into my forecast. And what I'm trying to predict, what we're trying to predict here is our 3-month rolling average of executed, right? So how much work did they do? So you can see here that the variables that are going into this are the previous months. Actually, yeah, so it's the previous month plus, here's what actually goes into the forecast. So D14 times H14. So we're using basically these variables over here. So we're using critical to customer dates, the database lock. We're using the, let's spread this out here. So number of database locks, critical customer dates, database lock A. I'm not sure what the difference is between those. F. And then the number of bugs and issues identified. So these are all are kind of feeding into this formula. And then the previous, it looks like the current month's rolling average too of available capacity. Right. So basically we have a multivariate, and I think head count actually feeds into this as well. So the goal here is to, whenever you're doing a forecast, you're trying to, and develop a model, you're trying to minimize the variance between your forecast and what the actuals, I'm going to hide these variables now, just so that we can see what I'm comparing them to. All right. So the idea here is to try to minimize the variance between what my forecast is and what the actuals ended up being, right? So the variance here ends up being, you know, what is it? M14 minus C14. So this is the actual executed. So this is the work that actually got done, right? So the variance ends up being pretty small on this one. So the trick on this is to make sure that you're comparing all of the same formula month over month over month, right? And it gives you an idea of a variance. It's a how accurate is my model, and it's going to be different from month to month, right? Like some months it's going to be really accurate, right? Depending on how good our data is and just how predictable our people were. And sometimes it's way off, right? Like how much did we, think we were going to get done? And we use this basically to kind of identify how much work is going to need to get done, right? So this is predicting, this forecast is like, how much work do we think we're going to have? And it's based off of, like I said, how many closes are coming up, how many defects are introduced, those kinds of things. And we make guesses on like our upcoming things. So some things we know about in the future, right? So now if these are all just actuals from things that have happened in the past, right? To judge the performance of our model. When you get down into future months, this is where the actual, I'm making an actual prediction now. I don't have an actual to compare this to yet. Right, so these variances this is all BS, right? These numbers are actually should be blank. These are based on an average of whatever. But the reality is we don't know what October, November, and December's actual executed capacity is. We just don't know. We know we can get a pretty good idea what the rolling average is going to be because we know some of the previous months, but we don't really know these either, right? So that's where this forecast ends up becoming really, really useful, because I need to know, based off of these other variables that I do know that in October, November, and December, I'm going to have 13 database locks. And I know that database locks are something that drive DCFs. The more database locks we have, the more DCFs we're going to have to process, right? So I'm taking that, and I know 13 database locks translates to X number of DCFs. So I need a head count, and I need people to cover that. Our normal staffing is 20 people. If I'm going to have 30% more, 40% more DCFs, I need X number of contractors, which is what this column is. So when I go to make the business case to Andrew for new hires of how many people do I need in the clinical data coordinator role to process DCFs, I can say, listen, I don't know exactly how many DCFs I'm going to get because I don't have that information. Nobody knows that, right? If you ask, no project manager can answer that question. Well, look at the project plan. There's planned hours. Planned hours is useless for this, because the planned hours, there's no way for anybody to know how many times a site is going to misrepresent something and then all of a sudden realize it and have to fix it, right? There's just no way to predict that. But I do know that on average, I have X number of closures means X number of DCFs and blah, blah, blah. And that means I need, I have this expected forecasted need for 10,000 hours, which means I need another 10 people. And is there some synergy there? Yeah, there is. And how good is my model? Well, I got a pretty decent model for predicting how many people I need. But you can see, so this is me holding myself accountable for how good is my staffing model. How far off is it on any given month? And I can only fill this variance number in after the fact. In fact, these are, down here in the future months, these variances are nonsense. They're just based off of this number here, which I don't know. In fact, I should just do that, right? Does that make sense? Any questions? So that's how to build a basic model without machine learning. All right. I'll pause there.
But how did you get to the weighted averages, the weighted
how did I
numbers?
decide what to weight
Yeah.
each variable? I
Yeah.
screwed around with it. I literally just played with the numbers to see how I can minimize this variance. So when you're judging the model, you look at your actuals. This is my test data set, right? And I basically take this number, right? Here's my total variance, right? Equals, let's look at the months, only the months that we have, that we know we have the data for September and before, right? So there's a couple different ways to do it. So you can sum your total variance for all of your historical data that you have. So this is judging how good is my model. Because I don't care how it performed on any one month, right? I care how it performs over time. And the best way to look at it across all the time in one quick and easy way is you just add it all together. So, and this would be the percent, right, total. And then I would even go so far as to say divide by Yeah, how many months do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We'll do, you know, normally you would only do 12 months historical, but we'll do 15 here because whatever. So my total variance, my percent variance, which is actually better than using total variance, because that could be way off depending on, the scale of the business changes. So percent variance is really what matters. You want to minimize this percent variance. Right now it's 10.18. This is a measure of how good my model off. Its variance month over month is off by 10% on average. Sometimes more, sometimes less, but on average, I'm usually off by about 10%. Right? So let's mess with our model. Let's say I think bugs and issues should be a bigger component for determining how many people I got. Let's make it 0.2. I think it's at least twice as important as I have it right now. I'll make it that 0.2 instead. So I make it 0.2 there. I copy it to all my other cells. Right? What's my average variance now? Oh my God, I destroyed it. That model's crap.
Isn't there a way to have a better way to get those weights from a statistical analysis or a regression or something?
Yeah, so it's multivariate analysis. And yes, the short answer is yes, there's a better way to do it. When you're dealing with a relatively simple model and the stakes are fairly low, and the variance is going to be pretty far off anyways, you don't spend as much time on it, to be frank. And you play with those weights until you get a variance that's within acceptable limits, and then you run with it. So so it was 10% right before. Let's see what it is now. Equals sum of, I'll just say, we'll just do 12. 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. All right. So before, when defects was at 0.1, it was 10%, and then I made it 0.2, and now it's 23% variance. So it's just not as good a model with 0.2. And you can get pretty refined, right? So like 0.9, I'll say, right? One more just to finish the demonstration. Oh wow, that really screwed it up, right? Now it's just total trash. So let's go back to our 0.1 that we had here. So there's an allowable limit of like how far off do you want your forecast to be, and 10% is not bad. The short version is like you also get an idea of how important each one of these components is by doing this, right? So like you would think this number of CTC dates is really important, but it's really not. The number of defects is the primary driver on this thing. And then also the historical component. All right, so to your question around is there a better way to find the weights? That's where the machine learning stuff comes in, right? What most of the machine learning algorithms are doing is they are automating and automatically testing this loss function. This is a loss function. It's a really crappy one, right? Not particularly sophisticated, but it is automated. It's essentially a test to say, what is the variance on my existing model and how good is my model? That's a test. and I want to minimize this number. I want to make it as small as possible. I would love to have a perfect model that told me exactly what's going to happen in the future. No such thing exists. If anybody says they have that, then they are doing a really simple physical phenomenon that is easy to predict. Right? But this is basically a loss function. So every single time in a machine learning algorithm like a neural net, what is essentially doing is coming in, tweaking the weight it has on one of these multivariate items, and then checking the loss function and seeing whether or not it is better or worse. If it's better, it moves the variable in one direction. If it's worse, it moves it in a different direction. And what makes some of those algorithms really fascinating is that the methodology they use for tweaking those variables. Some of them do them all at once. Some of them, because they're neural nets, they have multiple layers. This doesn't even qualify, this is a multivariate analysis. Neural nets add at least one extra layer of abstract variables in between the output, which is the forecast, and the input, which is here. An intermediate layer of variables that are not easily identified by a human being. They're just variable A, B, C, D, E, F, G, H, I, J, K, and they all take a weighted forecast output essentially from the input level, and they create a whole nother level of abstract variables that then are used in the exact same way for the output for the forecast or for whatever it is you're doing. And the way that it adjusts the weights inside of the neural net is it is basically, like I said, looking at the loss function. What is my variance? How accurate is my model on this run of the model? And is it better or worse than the last time? And that's where you get into Mr. Brownlee's. Switch back over to this here. Hopefully he has a chart in here that shows his loss function. No, he does not. So I'll just Google one for us. All right, here's an illustration of it. All right. This is demonstrating what I'm talking about. You can think of, any of these as a, let me know if I'm breaking up. I just got a bad network quality message. So this image here kind of demonstrates what I was doing manually with adjusting the weights. An automated machine learning algorithm automatically adjusts those weights for you via some algorithm. And these epochs are a one iteration of adjusting those weights and then checking the loss function. What's my variance now? What's my variance now? What's my variance now? What's my variance now? And you can see how much more effective a machine learning algorithm would be at doing this than I am in an Excel spreadsheet, right? You saw how long it took me to adjust the weight on one variable, right? This does 200, and it probably took this guy a couple minutes to run it. And you can see there's a low rate of return over time. It gets slower and slower and slower, and you get, less and less accuracy until eventually you reach a point where it just levels off and you're not getting anything out of continuing to adjust the weights. You reach the optimum. Does that make sense conceptually?
Yeah, that's one an automated way to do it, right?
Yeah, basically. So back over to Jason Brownlee. This blog post is one very specific algorithm that is used to do a regression forecast. It's a ridge regression. And the only thing that he's doing special, the only thing that makes this special basically, is he's giving you the loss function. Here's a different way to do a loss function instead of just using variance. What he's saying is, or what this algorithm is saying, is that you need to add a penalty, this L2 penalty, it's a level 2 penalty, that basically says the larger your coefficients are, the less the less, quote, accurate your model is considered to be. Why does that matter? He explains why it matters. I can't remember here off the top of my head. Oh, it has to do with the stability of the model, right? There's a thing in, evidently in statistics, that the larger your coefficients get, the more unstable your model becomes. Basically, it doesn't have what's called generalizability. It's not useful except outside of very specific scenarios. So if you want to build a stable model that's useful across sectional, like, you know, in various different usage cases, you have to have low coefficients, evidently. And as with everything in math, it's always a trade-off. Yeah. So that was a lot. There's a lot going on there in that conversation, that explanation. Let me know if I lost some people. I'm sure I did. So ideally, doing it for like the clinical data coordinator, going back over to my model, building a model for staffing for clinical data coordinator is here. So building a model for staffing for clinical data coordinator, I know what all from an expert perspective in my own organization on what impacts the organization and what the trade-offs are. I know what data I need in order to predict how many people we need. I think everybody has a little bit of an idea of like the things that go into this idea, this forecasting, right? You can see like these are actuals, and then the data set becomes forecasting at a certain point. But everybody kind of knows, they think they know what goes into this. You know, the number of people we have, where they're located, how many working days they're available, you know, those kinds of things. But then there's other things too that go into it that people don't even really think about, right? The how many transfers are scheduled, how many actually occur, right? There always ends up being basically two data sets that you end up working with: the forecasting data set and the actuals. The actuals is what you build it off of. The forecasting data set is what you actually get to feed into the model to see if you get a good prediction. So all of these items are things that I think most people that work in that organization would probably be familiar with and probably knew it impacted in one way or another. But the challenge that I have as a manager and that the leads have as a manager is identifying exactly how much it matters. How many data science setups are there? How much does that matter? How many people do I specifically need? And believe it or not, the clinical data coordinator role is one of the easiest roles probably to forecast, because what they're specifically accountable for is really easy to define. They're specifically accountable for DCF processing, CRs, and archival delivery. That's pretty much it, right? Everything else is gravy on top of that they do. But as far as what we get paid to do and how many people we're allowed to have in order to do it, that's it. So I only have to worry about those variables associated with those tasks. If I was to go through and try to do the exact same, and also because the volume is so large on those tasks, I'm able to get averages for how much time and effort it takes on some of those things and get pretty accurate on how many time and how many people and those kinds of things. As opposed to like an engineering organization, it gets really sophisticated, really complicated. And frankly, the individuals involved in the task are much more important than the averages or the overall delivery of the organization. Because as much as we might not want to admit it sometimes within our organizations, to do the same. I can ask engineer A to build a pie chart, and it'll take him an hour. And I can ask a guy with the same title, same responsibilities, everything. It might take him 6 hours. And because there's only, I'll say 5 in that team, who it gets assigned to is more important than the actual output of the team sometimes. And the ability to predict whether or not it's going to be on vacation, or whether or not there's going to be a crazy requirement of the development activity. Because let's be real, custom engineering and custom report development is never as simple as make a pie chart. It's always like, here's their 15 other I want you to do, and they have varying levels of complexity, and it's just virtually impossible to predict. So instead, what you end up looking at is like quality metrics, like how many defects are we entering, how often are we introducing, what's the severity, things like that, and make a case that way. So you need volume, you need consistency, and you need predictability if you want to build them. Those are key things that you have to have. And the larger the group or the larger the data set, the easier it is to get those things. So I could build a model for the BI reporting team, but frankly, wouldn't be very good. The accuracy would probably be way off. I challenge a video to do it. A video, you want to build a capacity planning model for me?
Yeah, by Monday morning.
All right. This is a really common thing that gets done in most industries. It's really easy to do for manufacturing in general, or for service industries. So if you're trying to figure out how many people you need working at your McDonald's, like, it's pretty easy to figure out, because you know how many hamburgers they sell a day, they know how many fries they send, they know those kinds of things. From manufacturing lines, you know how many widgets you're going to pull off the line, you know what the limits are, those kinds of things. When you get into custom software development and custom engineering, then it gets really, really impossible. It's more about the talent than it is the method. Method helps, but talent's more important. That's obviously my opinion. Anybody have any commentary, comments, anything? All right. Well, I think that's a good place to stop. Again, I would highly recommend this machine learning mastery website to anybody that's interested in this kind of stuff. It requires a certain amount of statistical background to get some of the stuff. But if you already have a relatively strong data or core statistics understanding, then it makes a lot of sense. And probably anybody in the data engineering organizations or the BI reporting groups could probably get into this pretty quickly, especially if you just start with the quick start guides and start doing tutorials. Quick start guides are where it's at, though, because they teach you most of the core concepts. All right. And it's free. All right, guys. Nobody has any other comments or questions, feel free to hit me up.
Thanks, Keith.
Always looking for help. Thanks, everybody.
Thank you.
Bye.
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 Bye-bye.